Hello everybody, I am Zach Peterson. Welcome back to my channel. Today we're going to be talking about some signal integrity software options that I like to use, and I often get questions about which one of these options is best. What we're going to do is we're going to take a look at two popular pieces of signal integrity software. One of them is Polar Instruments software, and then the other is Simbeor. Now, if you've watched any of the videos on my channel, you know that I am a user of both pieces of software, and one of the questions that I get is where exactly they fit in the PCB design process. That's what we're going to talk about today in this video. Let's go ahead and jump in and get started. So before we get started doing a full comparison of the capabilities of Polar Instruments and Simbeor, I actually want to talk about what these pieces of software are. Polar Instruments and Simbeor are both simulators, but they are not full 3D simulators like you would see with ANSYS or CST. Those simulators are intended for people who are setting up 3D simulation models, typically that have very complex geometries. Whereas Polar Instruments and Simbeor are highly optimized for PCBs and substrates. That's one of the things that makes them really powerful for PCB designers. You don't have to go through and manually build all of these 3D electromagnetic simulation models. It's actually already done for you in the software, and you can just get down right to the analysis that you need in order to figure out how to approach your design. Now, there is still a place in PCB design for the full 3D electromagnetic simulators. One of those areas, for example, is EMI simulations, where you can simulate conducted and radiated emissions as well as susceptibility. Another area is power integrity. Now, for example, Polar Instruments and Simbeor, they don't address power integrity, and full 3D simulators really do help you understand power integrity at a granular level. Another area is RF design, especially with antenna design. 3D simulators are great for RF design, especially when you have antennas. Oftentimes, you need to then calculate a radiation pattern or a gain pattern, and a full 3D simulator is going to allow you to do that. Polar Instruments and Simbeor are meant for the PCB designer that only focuses on PCB layout and routing, as well as stackup design. They are specifically tailored for those applications, and they occupy different portions of the development process. And so for that reason, you can really use all of them if you have the resources to acquire all the software. There are some things that Simbeor does extremely well that Polar can't do, and there are some things that Polar does really well, especially with respect to manufacturing, that you can do in Simbeor, but because they are more keyed into the manufacturing process in Polar, it's actually better if you're looking at it from a manufacturability perspective. So let's go ahead and jump into Polar Instruments and Simbeor, and we can really get a sense of the capabilities of these two pieces of software. So the first thing I want to do is take a look at Polar Speedstack. And Polar Instruments is really two pieces of software, two applications. One of them is Speedstack, the other is SI9000. And I've shown both pieces of software in different videos on my channel. Here inside Speedstack, this is a stackup design and documentation tool, and any CAD tool that is specialized for PCB design will allow you to create a stackup. Of course, you're going to need to do that if you're in Altium Designer and you're going to do anything in your PCB. But what's nice about Speedstack is it includes material information directly from the laminate manufacturers as a built-in library. So when you're creating your stackup in Speedstack, you can pull that information directly from manufacturers, and then you can export that as a report. You can also export it for use in SI9000. So that's one of the things that makes Polar Speedstack really unique. Other stackup design tools are really just graphical tools that let you arrange some layers and then output it into a format that maybe lets you use it in a different program. This actually creates a report that reflects the manufacturability and processing of these materials into a PCB stackup. And that's why this particular program is more meant for manufacturers than for designers. But of course, if you are a designer who is taking control of your stackup design process, it is beneficial for you to have a tool like this, because then you know that the information you are putting into your stackup accurately reflects the actual materials that your manufacturer is going to buy when they build your PCB. Now let's take a look at SI9000. So SI9000 is the sister application to Polar Instruments Speedstack, And it is also for designers because it does allow you to do some signal integrity calculations. But the important thing to understand about SI9000 is that it is a front-end analysis tool. It does not work from your PCB layout. So if you're going to do any of these calculations, you need to do them before you start your PCB layout, but after you already have an idea of what your PCB stackup is going to look like. So here you can see on screen we have a surface microstrip pulled up, and this tool allows you to calculate the impedance of this surface microstrip. You can see here that we have an entry for the substrate thickness. If I just change the substrate thickness to 6 mil, for example, I hit calculate. You see here it uses its internal model to then calculate what is the lossless impedance of this microstrip. Now, as you scroll through on the left panel, you can see a variety of different trace configurations, both single-ended and differential, and they do that because there are built-in models for each of these different configurations, which are then used to calculate the impedance. So that's really important. Again, you're not having to build these 3D models yourself like you would in a 3D electromagnetic simulation tool. You're using something that has been built in and validated against experimental test data, and that's what's being used to calculate the impedance in these models. Now here we're only looking at the lossless impedance, but of course all designs that have signal integrity considerations will experience some loss, and so that's why you need a frequency-dependent calculation. And that's what you'll find on this tab. So in this tab, you can do a frequency-dependent calculation as a function of your line length using any of those models that we saw on the previous screen. So here, for example, you can put in a loss tangent, you can put in a rise time. Here you can put in a line length. Just as an example, we'll do a 3-inch line, and then when you hit calculate, it will then give you the attenuation and some of the other parameters for this differential transmission line as a function of frequency. So you can see here, it's basically giving you the loss with copper losses and dielectric losses as a function of frequency up to 10 gigahertz. And of course, we can extend that frequency range if we like. Now, this is important because it's taking account of the roughness of the copper film that's in the stackup that's built into this model. You also have some control for configuring some of the parameters of that roughness model. Here you can see in the surface roughness area that we have some built-in models that are very commonly used in the industry to predict the effect of copper roughness and how it affects losses in your interconnects. Now, the other thing that we can do with this front-end simulation is we can, of course, look at the S parameters. And again, this is not looking at a PCB layout. Once you put this line into a PCB layout, the S parameters could be very different. But what this does do is it gives you an idea of the losses you might expect to see for this interconnect, assuming a particular termination impedance at the load and the source end. So here, if we're setting a termination impedance of, let's say, 100 ohms at the source, 100 ohms at the load, and we go ahead and click calculate, you see here its built-in model goes through and does all of these solutions. Now you can see here on this graph with the S parameter results that this return loss for this particular line is pretty unacceptably high. The peak goes all the way up above -4 dB. So that immediately tells us that this proposed design is not going to work in an interconnect that is terminated to a target impedance of 100 ohms at the source and the load. We can also look at the mixed mode S parameters, which is of course very useful because it lets you separate out common mode signal from differential signal. And that's something else that I've discussed in another video about length tuning. And you can get all of that data right here inside of SI9000. The other thing that you can do in SI9000 is sensitivity analysis. And sensitivity analysis is really useful because it shows you how your interconnect changes as you modify one of the parameters in this interconnect model. So for example, if I were to change, let's say the substrate thickness from 4 mil to 10 mil, and then I hold all other parameters constant, it will then tell me how does the odd mode impedance of one of these traces in this model change. So you can see here, if I just hit calculate, it's going to go through and run all of those calculations, and then it shows me that result both as a graph as well as in the table. So this is really nice. It shows me just how much variation in the impedance of one of these traces I could expect if we had our substrate thickness changing from 4 mil to 10 mil. That's really useful for analyzing things like manufacturing tolerances or what would happen if you were to swap out some materials in your stackup. There are some other things you can do inside of SI9000 as well, like for example, multi-line crosstalk. You can actually look at what is the forward and the backward crosstalk when you have multiple lines routed together, and that also helps you estimate the routing density that you can use in your design. You can then, of course, vary the stack up or vary things in the transmission line model like the spacing or like the trace width. And you can then resimulate and see exactly what the crosstalk is going to be. Again, this is really useful for estimating the routing density that you're going to use in your design, because you need to figure that out in order to set your clearance constraints when you actually get into your CAD software. So all of this kind of stuff is stuff that you could do on the front end before you've started your PCB layout. So now let's take a look at what's in Simbeor and see how it compares to all this stuff inside of Polar Instruments. Now I want to take a look at what's inside of Simbeor. And one thing to know about Simbeor is it is also an entire signal integrity suite, but it is more meant for designers and signal integrity engineers than it is for manufacturers. Now here inside of Simbeor, we can access some tools that are inside of a post-layout analysis. So you can see here I have an actual PCB layout brought up. You can see all of the components, and then you can see here we have a bunch of differential pairs in this layout. Now you can also do pre-layout analysis for via design as well as transmission line design. So you can see here I have an option to create a T-line model. I can then go through and create a model on my existing stackup. I can just kind of follow this wizard. If I want, I could, for example, create edge-coupled strip lines on one of my layers. I can just kind of click through here. You can see here it automatically calculates what is the trace width and spacing for a 100 ohm impedance. Once I just go through and click on all of this, it's then going to give me some results. And then I can see exactly what is the impedance and the attenuation of this transmission line that I just created in both common mode and differential mode. So that's extremely useful. I literally just click through a bunch of screens and you can already see some results here for the impedance and the attenuation. We can even do the same thing with vias. Here you can see if I just click on the via wizard, I just click through the screens. You can then see here, eventually we're going to get to a via analysis tool, and it's going to allow us to then simulate what is the S parameters of our via as well as the impedance of our via. So here I just clicked through all the screens on the wizard, but you can already see it's just immediately spit out some results using the built-in fast SI model for a differential via. So that's just a quick example of how easy it is to just load up and start building something with the built-in signal integrity tools on the front end before you start your PCB layout. Now, the real power in Simbeor, in my opinion, comes from the fact that it is also a post-layout simulator. And once you have your PCB layout finished, in order to get it into Simbeor, all you have to do is just export an ODB++ archive, and then you can import it into Simbeor and start doing all of the SI analysis that you need. Now here, as an example, we have some differential pairs in this layout, and maybe I want to simulate some of these differential pairs. So what I'm going to do is just select 3 of these, and before I even do any signal integrity simulations as far as S parameters go, I can just do immediately a calculation of the impedance of these lines using the stackup information that's built into my ODB++ archive. Now you can see what the output is here on screen for the differential impedance of these lines. You can see that these lines were designed to 90 ohms. The simulator tells you they come out to 90 ohms, so that's great. That's exactly what we were looking for in this particular design. Once we're ready to get the S parameters, we have 2 different options that we can use to model the S parameters using the electromagnetic simulation tools in Simbeor. One of them is the fast SI model, and then the other is a 3D signal integrity simulation model. And it is a full 3D model. But again, the real power in these tools is the fact that you don't need to go through and build a 3D electromagnetic simulation model manually like you might have to do in ANSYS or CST. All of those configuration settings are streamlined inside of Simbeor, so you can go through and very quickly build a full 3D simulation for this interconnect. And that interconnect could include vias on it. And that's another thing that's really powerful. Normally, if you have to do via simulations in 3D, again, you'd have to go into a tool like ANSYS or CST, and it's very time consuming to set up those simulations. Simbeor already has the tools built in to do that directly from your PCB layout. So just as an example with these 3 interconnects, let's go ahead and build an SI simulation and check out the S parameters for these interconnects.
A few moments later.
In order to set up this model, we're just going to click the extract button. We're going to select what we want to look at in terms of the S parameters. Here we want the insertion loss and return loss. We're going to look at pulse time domain response, and we might as well plot the pulse crosstalk while we're at it. And we're just going to go ahead and hit finish. And you can see here it goes through and it's running, and it's going to take a minute to finish. We'll come back when it gets done.
A few more moments later.
And 34 seconds later, you can see that we have all of our results. So our results are accessible right here inside the PCB layout, or of course you can go through and create some graphs that have all of these results as well. So let's go ahead and just kind of take a look and see what these look like. You can see here for one of these ports, we have the return loss right here. We also have the return loss for this port. We can go ahead and pin it so it stays open. And then we have a return loss for another port. So all the return losses are pretty similar. We can also go through when we create a graph, and we can then create crosstalk graphs, and that's going to show us what the expected crosstalk is between these lines. And of course, that is important because you can see here we're routing all of these lanes in parallel over a pretty long distance. And so it's useful to analyze the crosstalk in this type of situation with these differential pairs. We can also see the time domain reflectometry response. You can see here down at this port, we do have a little bit of reflection right at the input. And that does help explain what's going on in this return loss graph, where you can see the return loss rises up very close to 10 dB, but still stays within the acceptable range, although it doesn't give us a lot of margin at very high frequencies. So that could be a problem that we need to correct in this PCB layout. We also have all of the results here at the other end of the interconnect. You can see here, for example, what the TDR plot looks like at this end. You can also see, for example, the return loss. The return loss is pretty good starting from this end, which is at the BGA, and you can go through and bring all of these results on screen and analyze them. And again, if you wanted to, you could put them into a graph, or you can, of course, bring them up into full screen and take a look at what is the return loss in this example. Just like Polar Instruments, Simbeor also provides mixed mode S parameters, but it's doing it directly from your PCB layout. Now that's really important in a situation like we see here on screen, where we have these differential pairs coming out of a BGA region, and then we have to apply some length tuning. That length tuning can create mode conversion, and if there's too much mode conversion in this channel, the channel could be non-compliant with the interface standard. Mode conversion also creates jitter, and you'll be able to see the expected jitter in an eye diagram if you do an eye diagram simulation for these channels. There are some additional tools inside of Simbeor specifically for example, channel compliance. You can overlay channel compliance limits on your S parameter graphs, and then you can really see whether or not you're going to be able to be compliant with your channel interface standard. You can also see exactly what the level of margin is in different frequency ranges, and then use that to determine whether or not you need to go back into your PCB design and make some changes for signal integrity purposes. Thanks for watching this video, everybody. If you have questions about either piece of software or how I use them in my design and SI analysis process, make sure to leave some questions in the comment section, or of course you can find me on LinkedIn and send me a message there. Make sure to hit that like button, hit the subscribe button, and if you ask a great question, it might end up in one of these videos. We'll see you next time, everybody.